Okay, let's do a problem using the Impulse-Momentum Theorem. Sometimes this is also called the Impulse-Momentum relationship. It's the same thing. So the first problem, we have a boulder and it's rolling down a hill and then it crashes into a tree. So the mass of the boulder in this problem is 650 kilograms. And the boulder is moving with an initial velocity of 13 meters per second as it goes down the hill. And then it stops when it crashes into the tree, so our final velocity is 0. This problem is asking us to find what is the impulse required for this. So if we remember that impulse, we can find a couple different ways. One is its force multiplied by time. Another way that we can also describe impulse is we can also say it's a change in momentum. Now, anytime we have this delta, when you have a delta V or a delta P, then what we want to do is we want to expand that delta. So in this case, it'll be P final minus P initial. So final momentum minus initial momentum. Recall that momentum, that's not momentum, momentum, P equals mv. So what we're going to do for this is we're going to take what momentum is equal to, mv, and we're going to just substitute it in here and here. And we'll keep the subscripts for the final and the initial. So then we have J equals, that's our impulse, mv final minus mv initial. And you could leave it like this, or you know from your math class you can factor out that m. J equals m v final minus v initial. So this would be the equation that we can use for our first problem to solve for the impulse. Now we just put all the numbers in. We have our 650 kilograms, it's the mass of the boulder. Our final velocity is 0, and our initial velocity is 13 meters per second. So on the calculator we can do all this. We get a negative, right, because we have our 650 and there's our negative. And I have 8,450. And we have two sets of units that we can choose from. Kilogram meters per second is perfectly fine. Or we can have negative 8,450 Newton seconds. That's the other acceptable unit for momentum. So there's the answer for number 1. Number 2 is a similar question, but it's asking us to do one other thing. It's asking us to find what the force is equal to. So for this one, there's a car that's traveling. It's 1,200 kilograms. It's moving at 18 meters per second, and then it slows to a stop in 6.5 seconds. So let's list everything for this problem. The mass of the car is 1,200 kilograms. The car is initially moving at 18 meters per second, and then it stops, so the final velocity is 0. And it does this in a time interval of 6.5 seconds. And we're asked to find what is the force equal to. Now, if we remember from the first problem that we just did, we have two things that impulse is equal to. It's equal to force multiplied by time. It's also equal to a change in momentum. So then what we can do is we can set everything together that way. We'll say that impulse is equal to force multiplied by time, but it also happens to be equal to a change in momentum. And what we're going to do is we're just going to look at this part right here. That's all that we need. Let's rewrite this. F delta t equals change in p. And just like we did up on the first problem where we said momentum equals mass times velocity, we'll do the same thing. We'll take our mass times velocity and we're going to substitute it in over here when we expand those that delta p. So F delta t equals P final minus P initial. F delta t equals mv final minus mv initial. We could go through and do the same steps that we did down here that we did up to the top one in the first problem, and we can end up with something like this. We'd have ft on this side. We could also factor out that m and have v final minus v initial in the parentheses. But there's another trick that we can do. We can see from our listed information that our final velocity is 0. So it doesn't matter what our mass is. If we multiply it times 0, we get 0. That means that this term right here cancels. If I rewrite this, now I have F delta T equals minus mv initial. And we're almost there. We need to now solve this problem for force. So what I'll do is I'll divide both sides by delta T. We can see that the delta T over here cancels. I'm going to rewrite my equation over here so there's more room. On the left side I have F. On the right side I have minus mv initial divided by time. So this is our equation that we use to solve for force when we're using the Impulse-Momentum Theorem. Let's put the numbers in. Minus, the mass is 1200 kilograms. Our initial velocity was 18 meters per second, and our time interval was 6.5 seconds. You can use your calculator for this. Again, we have a negative sign right here because we're slowing down. So it's a negative force, it's a braking force. My calculator gives me 3,323, and remember the unit for force is the Newton. So this is how we do problems using the Impulse-Momentum Theorem. It's also interesting to note that this Impulse-Momentum Theorem is really just Newton's second law, and it's kind of hidden in disguise. So this just gives you another option to complete the problems, but it's not the only way. And unless a problem gives you instructions that says use the Impulse-Momentum Theorem, there are in fact other ways of solving these exact types of problems. I'll see you in class.